could have a do-over? How about taking a ride through time in the TARDIS with Doctor Who and Rose? What's the real physics involved with this? Is it possible? Can we go back in time? Could we go forward? Come with me, we'll find out. Whoa! Look at me! That was a time warp, wasn't it? Well, sort of. Here we are inside the TARDIS. What do you think? Science fiction, right? It's bigger on the inside than on the outside. That tells you we're dealing with science fiction. Let's see if we can sort out the facts. So the TARDIS, of course, is science fiction. Personal time travel, at this point in time, is also science fiction. Does that mean it always will be? Not necessarily. Think about 100 years ago. Would our ancestors even have been able to envision cell phones? That's amazing. And they're everywhere today. So how do we actually go about sorting through learning about time travel? Well, as with anything, scientists have to start small. When you're a baby, you don't necessarily run a marathon when you're a year old. You learn to crawl, you walk, you run. Scientists are doing the same thing. We've got to start small, and we'll talk about how we do that. First, we've got to learn just a little bit about how time travel might even be possible. Albert Einstein came up with a theory called the special theory of relativity. In that theory, he said, we're thinking about the world that we live in not as broad as we could. We're used to living in a three-dimensional world. If you take your hand and you move it on the desk, that's 2 dimensions. You're going up and down, left and right. If you take your hand and you move it around in a circle, but you go up at the same time, that's 3 dimensions. But there's a 4th dimension that might not be obvious. So as you raised your hand up in the air, that also took time, didn't it? We can't go back and do that over again. So how does that fit in with time travel? Well, let's think about that space-time connectedness that Albert Einstein talked about. If you think about a tablecloth, and you've got 4 people holding the edges of the tablecloth, and they're all pulling really hard, so it's nice and tight and it's really flat. If someone took a marble and rolled it from one corner to the other corner, it would go in a straight line. It would take a certain amount of time to do that. Now if somebody came along and took a bowling ball and put it right down in the middle of the tablecloth, well then the tablecloth would all be coming into a depression in the middle. Now if a marble was rolled from one corner, it's not going to go in a straight line. It's going to go in a curved path because the time it takes to travel causes it to go through space where space isn't flat anymore. So keep that in mind. We also have to think about some of the things that govern the constants in the universe, and one of those is the speed of light. The speed of light is the ultimate speed limit for anything in the universe. Scientists are trying to figure out how to make things go faster than that, but so far nobody's been successful. So how does that fit into time travel? Well, it means that time moves differently for different observers. Let's put it into some context we might be able to visualize. If you've got a snowboarder who's just gliding along on a flat snowfield, and let's say they have a tennis ball, and they take their tennis ball as they're gliding along, and they bounce the tennis ball off the snow and then catch it again. Well, to the snowboarder, it looks like that ball just went straight down and came straight back up. But if you're standing over on the side of the field and you're watching that, when the snowboarder bounces the ball to you is going to look like it goes in a path that is shaped like a V, because it has velocity both down toward the ground, but also it's moving forward as the snowboarder glides along. Well, if we think about it in terms of an ultimate speed limit and some basic math, speed in math is distance over time. If the speed limit can only be one set number, and something has to go a set distance, but 2 people are watching it happen, that means for one person, for it to go the longer distance, that clock ran at a different rate than the person who just saw it go straight down and up again. And it's kind of hard to wrap your head around, but that's the way it's envisioned. So wait, snowboarders clocks, do we have any proof of any of this? We actually do. Now, to start small, scientists have accelerated particles called pi muons that are really small, smaller than an atom, to very fast speeds, almost to the speed of light. And the pi muons have a limited lifetime. It's very short. But when they're accelerated up to that very high speed, they live much longer. In other words, they don't decay into other particles for a much longer period of time than they would if they were sitting still, as we would define sitting still. So we have some evidence that it actually can happen. On an everyday basis, ever used GPS system or Google Maps on your phones to get anywhere? Well, the satellites that signal has to go up and bounce off of and come back down to your phone, that takes a certain amount of time. Because those satellites are orbiting above Earth, and so think of Earth as the big bowling ball in space-time. It warps the space-time and causes clocks to run differently close to it. Well, the satellite's above that. So the clocks on the satellite actually run more quickly than they would down on the surface of the Earth. It's not such a big deal maybe, but it actually is. If you were depending on that satellite signal to tell you exactly where to go to figure out where you are and where you need to go and how many miles it is between there, the difference in the clock could make a big difference. And every single day, those clocks have to be corrected for that. Some of the weirder theories are the idea of wormholes. If space and time is this continuum like a fabric, well, if you took a piece of fabric, you could actually maybe wrap it around, roll it, and then if you had a big enough bowling ball or like a black hole, it could potentially make a tunnel between the two locations. So instead of having to go all the way around, you could just go through the wormhole. Problems with that, there's usually a black hole at the center, and anything that goes into a black hole gets pulled apart. So it would be a one-way journey for you. Not the best. Other weird theories are string theory, and in string theory, it has the possibility of many parallel universes. Think about this. 20 of you, each living your life in a separate universe. That's a little weird. Hard to wrap your head around. One thing about time travel that leads us to believe that we can't go back in time. Even though we might be able to go forward and move into the future with a clock that runs more quickly, we can't go back. Here's one of the paradoxes. Let's say that you went back in time and you accidentally killed your parent, so you were never born. But wait, how could you go back in time if you were never born? And it leads to these inescapable paradoxes that we've never seen anything like that, we have no evidence of that. So as far as we know, we can't go back in time, only forward. For now, what we do know is time can run at different rates depending on where you are. For now, we have to enjoy the journey in the TARDIS and pretending.